Hello everyone. In this session, I'm going to talk about predicting numeric values and one of the most important technique that is associated with predicting numerical values is the regression technique. So we would be spending some time in terms of understanding this concept of regression and how to predict the numerical values. Now just to draw something parallel, overall it's a supervisory learning process. In the supervisory learning, there are two broad headings. One is the classification models, where we are trying to predict the group of the values, and we have numerical prediction. So, in the under the classification, we have so many algorithms: k nearest neighbors, naive Bayes, decision trees, right? We have so many such kind of algorithms that are exist that we have already seen. We also have looked at classification rules, various things which are targeted towards the classification as a part of the supervisory learning. Now the other aspect of supervisory learning is the numerical prediction, where here I am going to look at one of the most important algorithm regarding the numerical predictions, which is the regression model. So we will try to understand what is this regression all about, and within this regression, the most popular form of regression is a linear regression. And again, within the linear regression, we talk about a simple linear regression. So we'll see what the simple linear regression is all about, and what is the role that is played by correlation in the process of regression. Then an extension of simple linear regression called as multiple linear regression. So once we get a basic hold on the overall regression process, we'll take an example and try to model the data and try to do the prediction as well using this regression as a mechanism. So just as a quick introduction to this world of regression, it's one of the most important techniques where my objective is to estimate the numerical relationships. So it's not a group predicting the group. I'm trying to estimate the numerical relationships among the various data elements. So one of the important measure of the numerical relationships earlier we might have looked at the correlation, which talks about the strength of the relationship between the numerical variables. The main objective of this regression analysis is I will use it to forecast numeric data. I'll use it to predict the numerical variables, and at the same time I will also look at the strength of a relationship. How strong is the predictor? How strong is a particular predictor linked with the dependent variable? What is the size of the relationship between the predictor and the dependent variable? So the regression actually identifies not just for predicting, but also it looks at the size and the strength of the relationship between the dependent variable and the various predictor variable. So if we have to simplify the whole process, it is defining the relationship between a numerical dependent variable, which is what we would be predicting, and one or more numeric independent variables. So all my dependent variables need to be numeric here, and so one dependent variable which is numeric, and n independent or predictor variables, they also need to be numeric. And regression as a process is quite comfortably used to model complex relationships among the various data elements. We are using various patterns between the variables, between the numerical variables. We are building a kind of a formula that is linking the dependent variable with the various independent variables, and based on them the forecasting can be done for a new set of variables. So we have a large number of methods that we can use for any kind of a machine learning task out here. Now, within this linear regression is one form of the overall umbrella of regression model. The linear regression is one such form. So we talk about logistic regression, we talk about Poisson regression. There are various other kinds of regression. So linear regression is one such form of the regression. Regression as such, as a definition, is nothing but it's a kind of a relationship between the dependent variable and one or more independent variables. So the only thing is, in case of linear regression, we say that the relationship between the dependent and the independent variable, it is following a straight line relationship, which means the equation that I am using to model the linear regression is y equal to a plus bx kind of a form, where y is my dependent variable, x is my independent variable. Now here it's a very important assumption that the dependent variable is continuous. The word continuous means it's a numerical variable. It can't be a class or a categorical variable. If it is a class or a categorical variable, then it comes under the heading of classification model. Whereas if it has to come under the heading of regression models, the dependent variable should be a numeric variable. Now in this a plus bx, b is the slope, a is the intercept. So by how much will my dependent variable increase or decrease when the independent variable x is increased or decreased by 1 unit? That is what is being indicated by the slope. And if the independent variable value is 0, what would be the value of the dependent variable is what is highlighted by the intercept. Now, this is the typical equation that we are trying to model. Coming to the world of machine learning, here my job is to identify what are the values of a and b such that the y equal to a plus bx line that is getting created, it is doing a very good linkage between x and y. So if I look at the values of x, the values of y, I plot all of them. This kind of a plot where I am plotting all the values of x and y, we call it as a scatter plot. Obviously we will look at it when we take up an example. Now I want to design one single line like this, which is having the best fitting between the values of x and y, which means the error between the various points and the line that we are drawing should be the least possible, least error. So that particular line is what we are calling as the regression line. Now within this world of linear regression, if there is only one independent variable x, then we call it as a simple linear regression. If there are multiple independent variables x1, x2, x3, so on, we call it as a multiple regression. And as I have already highlighted, there are various other forms of regressions also, especially if my dependent variable is a binary categorical outcome. If my dependent variable is a binary outcome, I can use a logistic regression. If my dependent variable is a count related variable, how many people die. So if it is more of a count related variable, I can use a Poisson regression. Now like this, there are many other forms of regression all these forms of regressions come under the broad heading of generalized linear models. So when we are studying the generalized linear models, it means that we are applying regression to various types of data, and in each of the types we are actually identifying the link function. What is the link between my dependent variable y and the independent variables x? So I would be giving a link function in the form of a mathematical relationship between y and x, which would be taken as a part of the input of the generalized linear models to come out with a regression model between the dependent variables and the independent variables. Now, as I have indicated, the first of its kind of regression, the basic preliminary one for us to have an initial understanding, goes with simple linear regression. So, we are trying to build a relationship between the dependent variable and single independent predictor variable, y equal to alpha plus beta x. Generally, the Greeks alpha and beta, if I am using, generally in statistical notation, I will use them to denote the parameters. So which means I have to estimate those alpha and beta. As I have seen even in the earlier example, the line cannot pass through all the points directly, but I want something that is a best fitting kind of a line. Right? When I am drawing some kind of a line, it looks like in some cases the predictions are lower than actuals. In some cases the predictions are higher than the actual. So we need some kind of a mechanism which will decide the values of A and B in such a way that the overall error, when I am looking at the error, it is the difference between the predicted and the actuals. So the overall error has to be the minimum most. Now this is where the process that was designed for that is called as ordinary least squares estimation. The alpha and beta are typically determined based on this ordinary least squares estimate itself. So they are chosen in such a way that sum of the squared errors of the residuals. So the residual is nothing but the actual value minus the predicted value. The actual value minus the predicted value. I am taking the square of the residuals and I am adding up all the residuals. So this is what is the sum of the squared residuals. My objective is choose the values of A and B in such a way that this sum of the squared residuals is as minimum as possible. And based on that, what typically comes out is the estimate of B comes out like this, which is nothing but each observation subtract of x subtracted from the mean of x. Each observation of y subtract the mean of y from it. Multiply both of them and sum up that product. Divided by each x independent variable, subtract the mean of the independent variable, square it, add it. In other notation, the numerator is actually called as the covariance between x and y, whereas the denominator is called as the variance of x. So the b is otherwise arrived at using the covariance between x comma y divided by the variance of x. So that's how the b is obtained, and a is obtained as mean of y. Now that we know the value of b, I take the mean of y minus b times mean of x, which will give me the value of a. Now this is the theoretical way of going ahead with it, but when I am doing this process in R, this whole regression model fitting can be done through a simple formula called LM. LM is nothing but linear model. So there is an automated way of handling all this thing quite comfortably in R. Here, one more thing that plays an important role in the understanding aspect of linear regression is the concept of correlation. Otherwise, people call it as Pearson's correlation coefficient also. So it's a one single number that indicates the strength of the relationship between the variables, especially the linear relationship. The strength of the linear relationship between the variables is what is measured through correlation. We can use a direct function called COR, which will give me the correlation between the pairs of variables. Generally, this value, theoretically, it is nothing but it is the covariance between x and y divided by the standard deviation of x into standard deviation of y. It ranges between -1 and +1. So if the value is close to +1, it indicates a strong positive correlation. Value is -1, it indicates a strong perfect negative correlation, negative relationship between the variables. Means if one variable is increasing, the other variable's value will decrease and vice versa. So a negative one indicates a strong inverse relationship between the variables. A positive one indicates a very strong positive relationship between the variables. But if the correlation is very close to zero, then I can very well conclude that there may not be any kind of linear relationship that is existing between the variables. It may be possible that there could be some non-linear relationship, but definitely the linear relationship is not present between the two variables. That is one thing that we can conclude by looking at the correlation coefficient. As quick ballpark figures, when I see the correlation in the range of zero point 0.1 to zero point 0.3, either positive or negative, we generally say the relationship is very weak. If it is in the range of 0.3 to 0.5, I can interpret it as a moderate relation, and anything above 0.5, I can really see that the relationship is much stronger between the variables. But at the same time, I have to understand that correlation does not necessarily say causation. It's only an association between the pair of variables. I cannot say if one has gone up, I mean if the correlation between the two variables is much higher, I cannot say that one determines the other. By knowing one variable, I can predict the other variable because they are not dependent on each other. Correlation does not talk anything about the dependency between the variables. It only talks about the level of association that is existing between the variables. Especially if I know in reality that one is dependent on the other, not through correlation. Theoretically, if I know that one variable is dependent on the other variable, then quickly I can look at what is the strength of the relationship between those variables. Is it a very perfectly positive kind of a relation, very strong positive or negative, or what kind of relationship is existing between the variables? So that's one thing that I can very well look at. The moment I know that this variable is dependent on the other variable. So this plays a very important role, especially in the context of multiple regression, where I talk about one dependent variable but many predictor variables that could influence the dependent variable. So that is what is multiple linear regression. It's an extension of simple linear regression. The only difference being there are multiple predictor variables, multiple independent variables rather than one single independent variable. So looking at the equation, the multiple linear regression comes out like this. Y is alpha plus beta 1 x1 plus beta 2 x2 so on beta n xn. So instead of just predicting the values of alpha and beta, here I have to predict the values of all the coefficients alpha, beta 1, beta 2, beta n. So again, the objective is minimize the prediction error itself. And theoretically, this is performed through the concept of matrices. So it will typically form simultaneous equations of n equations are typically formed in n unknowns, which would be determined through the inverse function of a matrix and the matrix multiplication. So theoretically, if I have to go with, this is the whole process that I would be using to find out the variables beta 1, beta 2, so on. But again in R, using the same LM function which we have used for simple linear regression, we can use the same for multiple linear regression as well. Now looking at the positives and negatives of this particular method before we take up the example. So it's one most common approach, especially if my data is a numeric data. If my dependent variable is more or less a numeric dependent variable, one of the most highly popular models for modeling the dependent variable is the multiple linear regression. Almost any kind of a data, the independent variables, though they need to be numeric, but even if they are non-numeric, if they are factors also, there is a way that the system will convert these, that the LM model will convert these factors into numbers, which is what we call as dummy coding. Right? We have looked at earlier. If a variable is a factor variable with n categories, we will create n minus 1 dummy variables which are binary. They will have a value of either 1 or 0, 1 indicating that this particular variable is having the value equal to that category. 0 indicates this particular variable is not the same as that particular category. So we don't need to create those dummy categories when we are using the LM function. The LM formula itself automatically converts all those factor variables into numeric by converting them into dummy codes. So along with the prediction model, it also talks about which variables are strongly influencing the dependent variable and by how much extent the value is significant. So we are talking about the strength of relationship between the dependent and the independent variables and the size of it as well. So which will help me to identify what are the 1, 2, 3 important factors that are playing an important role in the prediction of the dependent variable. Right? So that is how the relationship exists in a multiple linear regression. Now coming to the weaknesses part, this kind of a method actually makes a lot of strong assumptions regarding the data. Few things, it assumes that the dependent variable is majorly normally distributed. It assumes that the dependent variable values are normally distributed. So it's a very, very strong assumption regarding the data. And the model's form is not automatic. If we look at, it's not that I supply all the variables and based on the variables that I am supplying, the model will identify which combination of variables will be a good fit. Whereas in case of regression, that's not the case. I have to clearly give what is my dependent variable and what are all my independent variables. I have to specify them in advance. It's not that the model will pick it automatically. So that's one more reason I may have to be slightly careful when I'm working with a linear regression. If the data is having a lot of missing values, the models will not be developed for that kind of a data. And almost all the features need to be numeric. Of course, if they are not numeric, this dummy coding will come into picture, making them binary variables. So if the categorical, if I have so many categorical variables, obviously the dummy variable creation for those categorical variables is required, which means there is a slightly high amount of extra processing that is being done on the data. And at the same time, if I have to interpret the model, some knowledge of statistics is very much required. because we use some values called p-values, we talk of something called r squared, adjusted r squared. There are some kind of definitions that do crop up, which means some level of understanding of statistics is very much essential out here. So that's how the linear regression comes into picture, the multiple linear regression model. Now, once this conceptual aspect is there with us, we can very well pick up one example, a data set, and based on this we can very well try implementing the overall model and try to use that data for the prediction purpose. As we have already highlighted, the first step in the any model building process is collect the data. So I have taken the insurance related data, expenses relating to the medical expenses, etc. So that's the data that is stored out here. I'm loading that data. So we have to understand that in regression analysis, the relationship between the dependent variables and the independent variables, they have to be specified by the user, right? The modeler has to specify what is the relationship between the dependent variable and the independent variable. It's not automatically detected by the system. And at the same time, all the nominal variables need to be converted into factors. When we are getting the data into R, I have to make sure that all the variables which are nominal in nature, they have to be converted into factors. So we are collecting the data. So the basic preliminary checks that we are performing, look at the structure of insurance, which will tell me that it is a data frame containing 1338 observations, 7 variables. So it contains the age of the persons, which is in the form of integer. Sex is a factor with 2 levels, female and male. The BMI of the persons, it is showing some numbers. Then body mass index, the number of children for each of the persons is specified. Smoker status, whether he is a smoker or not a smoker. The region from which he comes from, northeast, northwest, etc. And the medical charges that are incurred. So these are the medical charges. So we have 3 factor variables here: sex, smoker, region. We have 4 integer, or probably we have 2 integer variables and 2 number variable, numeric variable. Now this is how our data is structured, right? So all these are factors, though they are categorical variables. When I have taken them into R, they are automatically converted as the factor variable. So I can really look at the head, which talks about the initial few values. So this is how the data is. A person whose age is 19, female, BMI is this much, smoker is yes, 0 children, southwest region, these are the charges, and so on. And at the same time, I can have a quick look at the summary of this particular variable. The summary is telling me for numerical variables, it will compute the minimum, maximum, mean, median, etc. So probably it looks like mean and median are more or less the same. So in case of age, I can very well assume that more or less the data is close to normal. The skewness is not very high in this kind of a data. Now sex is a numerical, is a categorical variable, factor variable. So that's where we are getting the count of the different values. This is the body mass index of the people, varying from 16 approximately to 53. Children varying from 0 to 5. Smokers, almost 1064 records are not smokers, whereas 274 are smokers. Region wise, we get almost uniform distribution across the 4 regions, but look at the charges. Minimum is 1100, maximum is 63,000. The mean is 13,000 with a median of 9,300. So there is a possibility here that the data may not be normal. There might be some level of extreme values. The mean is very much higher than the median when I am looking at the summary. So this itself could be an indicator that the data could be skewed. So I have to explore it further. So as a part of the exploration process, we have initially looked at the structure. So just seeing whether all the character variables are factors or not, whether all the numerical variables which we expect them to be numeric, they are numeric or not. So we are looking at the distribution of the dependent variable using the summary. We already have got an hint here for the dependent variable is nothing but charges here. So we have looked at the summary of the charges which said that the median is greater than, median is lesser than the mean, which is an indicator that there is a possibility of positive skewness in the data. If I want it a bit more further, load the psych package and use the describe function from the psych package, which will give you the skewness and other details as well. So I'll use the describe function of insurance from this particular package. Look at age, skewness is very close to 0, not too much of a bothering. Even in case of BMI, that's the same case. But look at the charges, skewness is 1.51, very much greater than 0, right? Not even in a range of 0.5. So it's a kind of indication that the data is not normal, but my regression model very much assumes that my dependent variable, it's assumed that the dependent variable is normally distributed. Now this is where probably the various options that I have, I can do a transformation of the dependent variable. Right, let me try out. So I can very well say insurance dollar ln charges, which are the log charges. Let me look at it as take the logarithm of insurance dollar charges. Right, let me take the logarithm transformation, insurance dollar charges. So this is what is my logarithmic transform. Now I really want to see the describe to see if the logarithm is slightly better. Looks like this. Skewness is almost 0. Kurtosis is also much lesser compared to the kurtosis that was there in the earlier case. So I would like to go with log charges for my model rather than the charges. So this is one more way. If my dependent variable is not normal, I would better prefer doing the transformation of my dependent variable. So later on we'll talk about some other kinds of transformations like Box-Cox transformation, which is a more generalized form of a transformation. But here let me just do the log transform, and now that the log transform has come more or less symmetric, I would not go any more further in terms of my investigation. So here the regression model requires every feature is numeric. That's anyhow taken care. We can also look at the histogram of the dependent variable. So I'll take the histogram of insurance dollar charges, which works out to be like this. It looks like more and more skewed, right? The high frequency is there in the initial values, but after that it has been following for coming down and down and down. So which is an indication that this is not normally distributed. There is no bell shape here. There is a lot of positive skew as a part of the values. But if I am looking at the ln charges, which are the log charges, right? If I am looking at the log charges, let me see what is the kind of histogram that's coming. This is looking more and more normal compared to the earlier case. So that's the reason I would be preparing the log charges as my dependent variable compared to the charges. So this is where probably insurance, I will update saying insurance of, I take all the rows, but columns wise I will delete the 7th column, which is the charges, so that I will go only with the log charges out together. So that's my first step, which I am able to identify as a part of the exploration of the data. Then I am also exploring the relationship among the features through the correlation matrix. So correlation matrix is actually trying to build the relationships between the pairs of variables. So generally this is built only for numeric variables, not for factor variables. So I can very well find out the correlation for each pairwise relationship. I can use a simple core as a function, right? I have to give within this core, I can't take all the datas, right? I am not interested in all the variables. I'm interested only in the numerical variables only. So this is where I can take the correlation of the insurance. I'll take only the subset of this insurance. Either I can specify the names of the variables, right? I can specify the names of the variables out here. So I will specify the C function where I am saying age is one variable, then BMI is another, then children is also my numeric variable. So let me take that children as well, and let me also take ln charges. This is also another variable. So I am taking the correlation between these variables. Okay, I think some bracket issue is there. See this bracket. Okay, correlation. So now I could see this is the correlation between the observations, right? Correlation between ln charges and age is 0.527, which is a positive correlation. And as we have discussed earlier, greater than 0.5, so it's a kind of a strong correlation itself. Whereas between ln charges and BMI, it's very weak. ln charges and children also is very, very weak. So these are the kinds of relationships that are occurring between the variables. The diagonal is always 1 because it's always the correlation of the same variable with the same variable. So it's always a perfect correlation. And you could see in the diagonals, in the other side there is a symmetry. Non-diagonals there is a symmetry. Because correlation between BMI and age is same as the correlation between age and BMI. So correlation of x comma y is same as the correlation between y and x. So that's where there is not much of a difference. There is no difference at all in the correlation, and the typical correlation table is always symmetric, right? So after finding out the correlation, we can also look at visualizing the relationship. Correlation is just a number, but the same thing, we can visualize the relationship in a graphical form, and for that we generally use scatter plot matrices. So it's nothing but it's a collection of scatter plots. Instead of plotting scatter plots separately for each x and each y, we can have it in a form of a grid. So it's a different collection of the scatter plots in a grid form. So in general, I will be getting the relationships between each of the variables. Just like this in a tabular form, you will get the scatter plot matrix as a table of the scatter plots, right? That is what we are calling as a grid. So you can very well detect the patterns if there are 3 or more variables, but only a pair is taken at a time. Now for that, we can use the pairs function. which is there as a part of the base R implementation itself, I can use the pairs function. Just like the way I have used core function, I can use the pairs function. So this is the pairs function that I am using. So I am getting the scatter plot. You could see this is between age and BMI. This is between age and LN charges. This is between age and children. Like that, you get between all the pairs. This is the relationship that is existing between all the pairs. So this is how the pairs function works. So the intersection of each row and each column. So this is age, this is age. So age, BMI, children, charges. So this will become, it's an intersection of age and BMI. BMI is there on the y-axis, age is there on the x-axis. So we are seeing that the age and BMI hardly there is any kind of a relation. But if you look at age and charges, as the age is increasing, it looks like the charges are also increasing. So we may find some kind of a positive relationship between age and charges. And that is what we could see even in the correlation out here, 0.52. So we can very well look at the different relationships that are existing between the variables in a graphical form using this pairs function. Then the more advanced form of representation of the pairs is there as a part of the pairs.panel function in the site package. Site package I have already installed, I have already loaded also. So that's where I'll use pairs.panel function. Again the same input. Pairs.panel, okay, did I not load the site? Oh, pairs.panels. Now you see slightly a better form of representation. Right, instead of just specifying the names in the diagonal, I get names. Along with the names, there is a kind of histogram in the diagonal, and on the upper side of the diagonal, I see the correlation in terms of numbers. Right, so here it is like 0.527, the 0.53 is shown here. So the upper diagonal, so you see the above the diagonal, scatter plots have been replaced with correlation matrix. So you see the correlation, pairwise correlation, age versus BMI, this is the correlation. Age versus charges, log charges, this is the correlation. So here we are seeing the correlations. Diagonal we are seeing the histogram along with the normality plot, or along with a smooth curve across the histogram. So joining the tops, so we have a kind of histogram that is being plotted, which is indicating the kind of patterns of each of the variables. Then below the diagonal we are getting the scatter plot, but again the scatter plot is not that same scatter plot. We have got something more here. We have got what is called as a correlation ellipse. It's a very interesting thing. Now if you look at age versus the log charges, the ellipse is a much bigger ellipse out here. The ellipse is much wider. So if the ellipse is much wider, we say that the correlation is stronger. Right? If you see here, between age and BMI, there is no ellipse at all. The black colored ellipse is not there at all. So which means the correlation is not at all existing. Whereas in the other cases, the ellipse is slightly more like a circle. So the more and more it's a circle, I could see that the correlation is lesser. The more and more it is becoming an ellipse, it means that the correlation is increasing. So I could see between age and log charges the correlation is much higher because it's a correlation ellipse that is clearly formed. So understanding wise, correlation is nothing but it's a visualization, correlation ellipse. It provides a visualization of the strength of the correlation between the values. In that we have a red dot. So it is actually the mean of x and mean of y. This is the red dot. The mean of x and mean of y intersection is the red dot. So where x and y are intersecting, that point is what is called is represented through a red dot. And if the ellipse is more and more stretched, we say that the correlation is high. If the ellipse is not at all stretched, we say if it is more like a circle, we say that the correlation is almost negligible. So that's one additional information that is being provided by the pairs.panels function, which is an improvisation of the scatter plot. And along with that, we also have a Loess smooth. Loess smooth is nothing but the red line. You could see here it's a straight line. Here also it's a straight line. Whereas here it is looking like a curve. Whereas here also it's a straight line. So the more it is looking like a straight line, I can say that the linear relationship is more apt between x and y values. But the moment I am seeing this kind of a curve, I can say that the linear is not apt for this. I should look out for some kind of a non-linear relationship in the data. So here I could really see how about looking at age squared or some kind of non-linear transformation of the age, because I am seeing some kind of a curve in the relationship. So that will give me some additional pointers to improvise the data, improvise my model. So correlation ellipse will tell me the strength of the relationship. Along with that, I could also see the Loess smooth, which is a curve that is drawn on the scatter plot, indicate the general relationship between the x and y. Is it more and more of a straight line relationship, or is it more of a non-linear kind of a relationship that is existing between the variable? So that's the next step, the next important point that we have to understand. Now, moving on to the next step, now that I have my data in front of me, I have to go ahead training the model. So it's better that I take out a sample of data, create a training data and a testing data. Okay, so let me do the splitting. What is the total number of rows? N row of insurance 1338. And what about the 70% of it? 936. So 937. Let me take 938. It would be round figure 400 falling into the test category. So I'll take 938. Okay. So let me call the set.seed. I'll take it as 1000. I'll use the same model for others as well. So that's where let me remember this. Train. I'll take a sample 1 to 1338. I want a sample of 938 observations as a part of my train. So I want to randomly pick out 938 observations between 1 and 1338 and where the replace equal to false, no duplications at all. So based on this, I want to get my training data, which is nothing but insurance. I'm taking a subset of it, train rows, all columns. This is my train data. Then I have the test data, which is also insurance, where I'm taking minus train rows and all columns. So I have my training data, I have my testing data as well here. Now, once I have my data, I can build my model. I'll use my LM function. So I'll use LM. So let me store this, right? uh, model 1, I'll use lm function. The dependent variable for me is ln charges. Independent tilde, independent variable is all others, I will call them as independent variables. So that's where I'm putting it as a dot. Then the data, I will specify it as train data. So I'll specify this as a train data, a model will be created and I would be storing this model. lm function, where I am giving it as model 1, lm dependent variable, tilde independent variables. If I have a few set of independent variables, then I'll specify them as a plus b plus c. And if I also want to consider the interaction effects between the independent variables, then I should mention it as a star b star c, wherein it would take a plus b plus c plus ab, which is interaction between a and b, plus bc, interaction between b and c, ac, interaction between a and c, abc, interaction between three-way interaction between a, B and C. So that is what will come out as A star B star C. But otherwise, if I want to consider all the variables separately, I am simply giving it as dot. So it's a regression model object that I am going to get, which we would be looking at, and we would be using it for making prediction. So the dot character is what I have used if I want to take all the features as a part of the model. Now my model got created out here. So I'll type in the name of the model to see what it actually contains. I'll get the coefficients. So you could see it is saying this is the formula that you have used. The coefficients are like this. So with respect to intercept, it is 7.032, whereas in case of age, it worked out to 0.0338. Similarly, we say sex male is minus 0.052 and so on. Now, why did it create sex male? Because sex is a factor variable. Then, because it's a factor variable, it has converted that factor variable into a dummy variable. Now that factor has two categories, male and female. So it has taken male as another variable. Sex male is a new variable that is created, which will have a value 1 if the person is a male. It will have a value 0 if the person is a female. So it's like male or not a male. And by default, not a male will be taken as a female. Similarly, for BMI, this is the coefficient. For children, this is the coefficient. For smoker, S, this is the coefficient. For region north, now in the region there are 4 categories: north, southeast, northwest, southeast, southwest, and something else. So because of that reason, each one has been created as one other dummy variable. So because there are 4 regions, 3 dummy variables got created. And what we could see is the coefficients indicate the strength as well as the size of the relationship between the variables, as well as your dependent variable, which happens to be the log charges. So you could say, just by looking at this, the charges increase with respect to age. So the higher is the age, the higher are the charges. The charges are increasing with respect to BMI. More the number of children, the charges are increasing. If the person is a smoker, the charges are increasing. But if the person is belonging to northwest or southeast or southwest, the charges are actually decreasing. And even if the person is a male, the charges are decreasing compared to that of a female. So for females, the charges are slightly higher compared to that of male. So this is some kind of basic understanding that we have got regarding the model. So in practice, the intercept is generally not considered for the interpretation purpose. And you see that the LM function, automatically has created the dummy coding for all the factor type variables. So if there are n categories, only n minus 1 dummy variables are created and one of them is always left empty. So that's the next step. And if I want more details regarding the model, it's better that I type summary of model 1. So wherein much more details are coming up. So we will look at the evaluation of the performance of the model using this summary. Because when I am looking at the parameter estimates, they are only talking about the relationship between your parameter, between your various variables and the dependent variable, various predictors and the dependent variable. So which ones are positively impacting the dependent variable, which ones are negatively impacting the dependent variable, and so on. But when I am looking at summary, the summary will give me the overall performance of the model. So these are the coefficients that we have got even in the earlier case. This table, if we see the estimate column, this is same as the one that we have got earlier. So it's as good as if I really want to create a formula out of it. It is like log charges is equal to, I'll take this 7.073 plus 0.033 times age of the person, then minus 0.052 times 1 if the person is a male, times 0 if the person is a female, plus 0.013 multiplied by BMI of the person, then plus 0.104 multiplied by number of children, etc. So it actually goes this way. This is the model that is typically getting created in the process. So that's the summary. When I am looking at the first section of the summary is residuals, which talk about when I am doing the prediction, right, when the same model is applied back to the same training data, I see that the minimum most error was minus 1.11. The minimum most error was minus 1.11, whereas the maximum error was 2.11. So that's the kind of a difference that is there in the prediction. So there is a possibility that some of them are not predicted properly at all. And if you see the quartiles, which is the middle 50% of the observations, I don't see too big a difference, right? So the first quartile is minus 0.2, median is minus 0.05, which is approximately around 0.15 difference. And from the median to the third quartile also, it's approximately 0.11, 0.12 difference. So the difference is not that heavy there. But the bottommost 25% and the topmost 25%, I see much bigger residual. So there is a possibility that some extreme observations might not have been predicted by the data properly. So the residual section provides summary statistics for the error in the prediction. So you could see that in some cases the error was much higher, which is like the way we are measuring it is the actual value minus the predicted value. So there is a lot of under prediction here and there is a lot of over prediction here. So the model is not that perfect. There are some kind of loopholes that are there as a part of the model. And if I have to really talk about the formula for the model, this is the formula. And the other thing, you have to actually focus on the stars out here. So you could see here it's a significance levels. 0 means 3 stars. So if it is significant at 99.9%, then it is 2 stars. Right? You could see all these things. Then if it is a single star, then it is 99%. If it is a dot, it is at 95% and so on. Now you could typically see these are all 3 stars, which means they are very, very significant. So the moment I am seeing even at least a single star, I could see that the variables are significantly impacting the dependent variable. The higher the number of stars, I could see that they are significantly impacting, and the lesser the number of stars, their impact is slightly lesser. So probably you could see the gender is not that highly impacting the dependent variable, which is the charges. So which means the charges are more or less similar across the males and the female. And similarly, the region belonging to northwest is also not that significantly impacting compared to the base. So we can really make out which variables are significant and which variables are not significant. So the stars are indicating the predictive power of each of the variables. How likely the value is close to 0. That is the significance level. Right? How likely the coefficient is going to be 0. So if they are stars, it means that it's very, very unlikely that these values are zeros. It is very much away from 0. All these coefficients are, though this is 0.01, it says this is very much away from 0. It's nowhere closer to 0. There is only a 4.82 into 10 to the power of minus 7, which is 0.000000482 chance that the coefficient of BMI could be 0. So there is a very, very limited chance that any of these coefficients can be equal to 0. So that's the reason all these variables are very much significant. Generally, we compare it with 0.05. So if I get this probability of greater than or equal to t, which is in common man's language we call it as a p-value. So if the p-value is less than 0.05, we directly take it as the coefficient is significant, and if the p-value is greater than 0.05, then we say it is insignificant, and there is a possibility that this range will contain even a 0. So those variables generally we don't include as a part of our model. So if the model is having very, very few features that are significant, here of course almost all the features are looking significant, but if the model is having very, very few features that are significant, then I really need to relook at the model, try to identify a new set of features, try to do some more additional work before I use the model for the prediction purpose. So that's one more interpretation that I can do by looking at the model. Then the multiple R squared, 75.06%. So this is the current accuracy of the model. So this is the measure which says how well our overall model explains the dependent variable. So what proportion, what percentage of the variation in the dependent variable is taken care by the list of all the factors that we have given to the model? It's coming out as 75.06%. Now if I can find out any other model which can still increase the R squared even more further, that kind of a model will be more and more preferred for me. So if it is coming out close to 100%, then I can say that whatever the data that I have taken, whatever the features that I have taken to predict the dependent variable, that set of features is perfectly explaining the variation in the dependent variable. But of course, there are a few more drawbacks. Again, if you look at the theoretical readings associated with each one of them, we will see that the more and more new variables you are adding, right? If right now you have 8 variables, so you add one more variable to it, the 9th variable, it is very much assured that the R squared will be always higher than the R squared of this case. So R squared will keep increasing with the number of variables that you are adding to the model. but by what extent it is increasing? Is it a real significant jump? Now, to understand that, there is some basic manual calculation that is performed called as adjusted R square, which is like a small penalty that is being applied for the additional variable that you are adding to the model. So if after removing that penalty, the R squared is still higher, then I will still say that new variable that I have added is contributing significantly to the model. But if after removing the penalty, if the R squared is lesser, then I say that the model is not improvised because of the addition of the new variable. So there is no point in adding the new variable at all. So generally when I have to compare two models regarding which one is better, we prefer using adjusted R squared as the mechanism. So that particular model which is having a highest adjusted R squared will be used for comparison purposes rather than the one that is having a higher R squared. So right now the R squared is 75%, adjusted R squared is 74.84%. So we'll see at a later point when I do some other kinds of models. I would like to actually do a regression tree also for the same data. I want to do a model tree also for the same data, and probably some other models at a later date also on the same data to try to see which one is coming out to be much better estimate. So if I want to improve the performance of the model, one, I need to have a subject matter knowledge in terms of understanding which other variables could contribute to the decision variable. Did I omit any of the variables? Are there any other kinds of relationships that are implementing the decision variable differently, which could improve my R square? So we can use this information in the model specification. Let's say along with age, I want to see even if age squared also plays an important role, right? So I want to add that kind of a relationship also as a part of my overall model. So I want to really make some kind of modifications like that to typically see if there is any kind of an improvisation that I can bring out. Let's say I want to bring in a model 2 just for understanding. I'm taking all the variables. Along with that, let's say I'm also considering age square. All other things remaining the same. Now, if I look at summary of model 2, okay, if I am doing like this, then it is actually considering star plus age squared means for every observation, I think it is adding up the age squared. So what I can very well think of doing is add one more column, right? Better, that would be better. Insurance dollar age 2, I'll take it as insurance dollar age square. Now let me try my model 2, right? So in this I really don't need, okay, I'm making the change to the insurance, but I'm not making change to the train data, right? So let me take, okay, so let me just check head of train data now. So it does not contain the square. So I have to do the same thing. Train data dollar age 2, I have to take it as train data dollar age squared. So that's how I am getting my train data dollar age 2. So based on this, I will again rebuild my model 2, where I don't need age squared. Now let me look at the summary of model 2. So now you could see age 2 is also added, but R squared went up from 75 to 75.12, but adjusted R squared becomes 74.88, whereas here it is 74.84. So I could see that the adjusted R squared did not change at all, so I don't need to consider the age 2 at all as a part of the model. So that's how we actually play around with the stuff. So insurance, let me just check now. Dim insurance, if I'm looking at, it's 8. So I'll remove the last column, insurance minus 8, all the rows, and minus 8 column. Similarly, let me do the train data as well. Train data also, I'll take it as train data, and I'll remove, and I'll take all the rows, I'll remove the 8th column even from the train data. Fair enough. So I'll use my existing model itself. But that is one way I can do the modifications. I can introduce non-linearities, etc. But my intention is increase the R squared, increase the adjusted R squared. So do necessary transformation. Sometimes instead of taking the data in the same form, I may want to take logarithms, I may want to take all the other kinds of effects. And in some cases, I may want to even bring in the interactions between the elements as well. So all these things I can very well do, and finally see in which case my R squared is actually getting increased. Now here right now our R squared is gone up to the extent of 75%. So I can very well use this to do the prediction for my test data. So let me use that prediction. I'll say pred, where I am using predict the model 1. I am doing it on my test data, and here I am considering the test data. So based on the test data here, I am getting my pred values. So these are the pred values associated with my test data. I can very well find out the correlation that is existing between the pred and the actual, which is the test data dollar ln charges. I am trying to find out the correlation between the two. Here it's coming out to almost 90%, and the correlation squared, which is what is your R squared, is coming out to 81%. So when I am trying to do this prediction for my test data, approximately it's coming out to 81% accuracy. So I can very well think of using this model for doing the predictions quite comfortably. So that is how we work with linear regression. We first create a model, and then based on the R squared and the adjusted R squared associated with that model, we'll use the model for the prediction purposes. So I hope you got a basic amount of comfort level in terms of using the regression model, creating the regression model, understanding the output of the regression model. If you have any further queries regarding the same, you can very well get in touch with me by giving me a call on the number that I have provided below, or you can even send in an email at the email address that I have given below. Thanks a lot for listening to the session. Thank you very much.